So here, myself, Dr. Padmavati, I'm going to cover today's session. There are various. We have seen a few queries which have been posted by all the participants. So we will be covering those queries first, and later on I'll be taking you the overview of the course till now, whatever has been covered, right? So in one of the query, it was mentioned that what type of textbooks to be referred for mathematics. As we are covering in deep learning, we will be referring linear algebra, and as well as one of the like courses, like you can say that calculus, derivatives, even matrix operations are required. So for that sake, I suggest you to go through very like basic mathematics book, right? And in that, with that, let's take the second query. The second query is with respect to the main difference between machine learning and the deep learning, right? And what type of metrics to be used for this. So in this particular case, what So in this particular case, the first and foremost difference is what is the difference between machine learning and deep learning. The difference between machine learning and deep learning is in machine, we have to have hand features, right? And whereas in deep learning, hand coding is not required. The machine will learn by itself. And deep learning itself is a sub-part of machine learning, right? With that, let us try to understand the subsequent question, that is what type of metrics can be used for deep learning. So let us try to understand what type of problems can be solved using deep learning, right? And later on, we will see various other metrics. Initially, what is meant by problem of deep learning? What type of problems the deep learning deals with, right? So initially, deep learning comprises or solves two categories of problems. One is the classification problem, the other one is regression problem. These are the broad categories with which we can solve any kind of problem with the help of deep learning, right? So first thing, what is classification? Classification is nothing but suppose if we have some kind of problem. For example, given a set of images belonging to cat image and dog image, we would like to categorize whenever I give the input as which belongs to cat image. Okay, whenever I give this as an input to the model should be able to predict, yes, this example belongs to cat example. Okay, similarly, if I provide the dog's input image as an input to the model should be able to classify it correctly as is the given input belongs to dogs category, right? So this example belongs to classification, and in particular classification example, in particular it is binary example, right? The model is able to tell you whether the example belongs to cat image or the dog's image, right? So we call it as a binary classification because the model is able to categorize whether 0 or 1 inside the image, right? In a similar way, suppose instead of only two categories, if I want to check what type of digit the person has written, okay, that is digit classification problem. In digit classification problem, most of you might have started with the MNIST data set for deep learning in order to solve the problem using deep learning. So the MNIST data set is designed for solving multi-class classification, where given the digit, the model should be able to tell which digit is this, right? Whether the digit input image comprises of 0 in it, or whether the input image comprises of 1 in it, or what, right? So if my model is able to tell exactly whether the given input image belongs to 0, 1, 2, or up to 9. So we can say that this particular model or this particular problem belongs to multi-class classification. And again, in particularly, if I need to tell how many classes this problem categorizes into, it categorizes into 10 different classes, right? Moving on to the other set of problems, that is regression problem. Suppose if we wish to find or predict what would be the price of the house, right? So in that case, what would be the different kind of input that it should consider? It should consider different kind of inputs. For example, in which particular locality is the house located, and how many number of rooms does it have, and so on. So depending on different features of a house, I can be able to predict the price of that particular house, right? And this example itself is a prediction problem or a regression problem, right? Now, given different type of problem, whether it is a classification problem or the regression problem, we do develop deep neural networks, right? In deep neural networks, suppose we have the set of activation function which are being used, right? There are various activation function which are being tried, and most widely used are sigmoid function, and even some of them they do use in particular logistic regression, and or else the tanh function under sigmoid function, the sigmoid family of functions. And even some other authors, they do use ReLU activation function, and leaky ReLU again is one of the most widely used activation function, right? And mainly these activation function which I have named are basically used for the hidden layers, correct? What about the output layer? What type of activation function need to be used at the output layer? In the output layer, we can use like again, what type of problem are we solving? Okay, suppose my output is having some probability based output. In that particular case, we can go for using softmax function as the activation function, right? Whereas suppose if my output neuron does have some kind of uh, real valued output, right? So in that case, I can use simple linear function as my activation functions, right? And moving on to computing the pre-activation and activation function with respect to each of the feed-forward neural network. Let us say in feed-forward neural network, we have been given input image inputs, input layer, we have been given output layer, and we have in intermediate hidden layers. We can use n number of hidden layers depending on my own requirement, right? And in particular, as I explained earlier also, in the hidden layer, we can use sigmoid function, family of sigmoid function, or ReLU, or the leaky ReLU activation function, whereas in the output layer, we have to look into what type of problem we are solving, right? Suppose we are solving the problem which belongs to the kind of real valued output. In that particular case, we have to go for using the linear activation function. Otherwise, we have to go for using softmax activation function. right? In this particular case also, once we do forward propagation, we have to check how far our output is uh, with respect to the real output. What I mean by that, suppose we are doing the forward propagation, and in that particular case, we have been initialized some weights randomly, weights and bias values randomly, and I do compute the pre-activation with respect to each layer, okay, and activation on top of it. Once we compute pre-activation and activation function with respect to each hidden layer and also on the output layer, we will be able to predict the output. Okay, we will be able to get some output y hat, and we want to see how far we are from y hat, from actual output, right? Actual output we usually represent it as y, whereas the predicted output or the computed output we represent it as y hat, and we want to check how far y hat, how close y hat is with respect to y. Okay, in order to do this kind of computation, again depending on the type of problem that we are solving in, suppose I am solving the prediction problem or regression problem, in that particular case we have to use sum of squared error, right? So mean sum of squared error case, type of loss function. Whereas if we are solving some kind of multi-class classification problem, right? So in that particular case, what type of loss function we have to use? We can use the cross entropy loss function. With that, we can check whether whether we are doing it. Suppose I am solving class classification problem, and my actual output says, or actual output is, it says that the problem belongs to class 1 category. Whereas if my predicted output says, whatever computation we have done based on the computation, if my output is giving the computed output, it is giving it as the problem belongs to class 2 category. So there is a mismatch, right? So in this, what we have to do is we have to compute the, we have to check how far we are from the actual output. So again, we will be using cross entropy loss function, because this example belongs to multi-class classification problem, right? So once we do that, later on what we can do is we can use based on the back propagation algorithm that has been discussed in this session. So based on back propagation algorithm, we can compute, we can update the weights, right? How do we update the weights? In case of feed forward, let us say feed forward neural network, we have discussed that we can update the weights by using the back propagation algorithm. So how do we achieve that? We have to use the most widely used again algorithm is, how do I update the weights are based on the gradient descent algorithm, right? So in the gradient descent algorithm, what we have to do is, suppose I have 10 different examples. Okay, let us say 10 different on 10, based on the 10 different examples, what are we doing? We are able to tell, or we are able to compute the gradients, or we are able to update the gradient. In each iteration, we are taking multiple iterations, right? We are solving the problem with the help of multiple iteration. In each iteration, what type of problem we are solving? We are taking all the 10 examples, and I'm going to compute the derivatives, and later on we are going to update the weights again based on that formula that we have discussed. W is equals to W plus minus eta of the gradient that we have computed, right? So based on this particular formula, we are updating. Now, how many examples we are seeing before each update? In the batch gradient descent algorithm, okay, we are we are using all the examples in hand. Okay, all the training examples, based on, we are processing all the training examples, and then we are computing the gradient and we are updating the gradients, right? Now, in each iteration, we are doing this activity, right? If we follow this particular strategy, definitely we are going to reach to the optimum values, right? But the way we are computing, we are considering all the examples in hand. For that sake, it will take a longer time to reach to the optimized values, right? So many authors, researchers, they tried different versions of update rules. For example, in few of them, they considered, instead of considering all the example, let us consider only one example each for each update. And this belongs to category of stochastic gradient descent algorithm, right? So in stochastic gradient descent algorithm, we are updating the gradients, we are updating the weights basically based on single example, right? So if we use this stochastic gradient descent, we may reach the optimal, near optimal values. Maybe the time it takes maybe very less, right? But the way we are doing the optimization of the update we are doing basically based on single example, right? So for that sake, there will be more fluctuations when you check the output, right? So one of the examples says you take the gradient in this particular direction. The other one says you try to update in this particular direction, right? So there will be many oscillations in case of stochastic gradient descent. Whereas in simple batch gradient descent, the time it requires was very, very high for a single update, because there we were considering many examples. Whereas in stochastic gradient descent algorithm, we are considering single example, and based on single example itself, we are trying to update the gradients, right? Whereas update the weights. Whereas we have some sort of intermediate algorithm, that is, it neither considers all the examples nor it considers single example. How it updates based on some mini batch gradient descent algorithm, right? So it takes the it considers the entire training set as the training set, and it divides into multiple mini batches, and it considers, for each update it considers one set of mini batch, right? So using this, the oscillations, the one we were able to see in the many fluctuations in case of stochastic gradient descent, will not be there anymore. And even we will be able to reach the optimal values in a decent time, right? So again, there are many variations with respect to gradient descent algorithm, batch gradient descent algorithms, okay, which have already been covered in the lectures. You can go through them, right? And the next one was with respect to uh, bias versus variance trade-off. Right? What is bias versus variance trade-off? Let us look into it first. Suppose we have some examples for we have uh, we have to solve some example, right? And in order to solve the example, we have used a very simple model, right? So in that particular case, the model that we have used is very, very simple model, maybe very linear model we are using even for non-linear problems, right? So in that case also, in case of simple model, as my output is is not accurate, or I mean to say my output, whatever my output my simple model is predicting, is not as close to my actual output, right? So it varies very much with respect to actual output. But suppose if we consider let's say two different models, and both of them they are very simple model, and both of them we are using simplistic model in that. For that sake, the simple models, the first simple model and second simple model, the difference between, or the whatever output that they are predicting will be very close. Okay. Definitely they are not closer with reference to the actual output, because actual output is not using the simplistic approach that these two models are using, right? But when we see how close the first simple model and second simple model, both of them they are giving almost same result, right? In that case, we say that variance is very low, whereas both the models they are actually very far off from the actual values, right? So for that sake, there it introduces the high bias, right? So in general, simple models do have high bias, whereas very low variance. Whereas suppose my if we propose the model, and the model is very complex in nature, right? And whatever training example that we are training, right? And that my complex, as my I am using very complex model, it tries to fit exactly the training data, right? Now if I develop two different complex models, in that particular case what happens, the two different complex model, definitely they have been trained on their own set of training examples. Now whenever we are giving any kind of input from that particular training example, then it is giving the correct result, right? Suppose we are giving unknown data to any of those two complex model, in that particular case their behavior will vary, because in complex model it has learned the set of training example very exactly the way we have introduced the, I mean to say, we have introduced training two different training examples, or two different training sets, one training set for the first complex model, whereas the second training set for the second complex model, right? Now what happens, whenever we are feeding the data within that particular training example, then definitely it is giving us the correct results, right? But if I vary a little bit, and if we give the unknown data to any of those complex model, then definitely as it has not seen that unknown data during its training, so for that sake it will not give the correct result on the unknown data. Both of the model will not give the correct result on the unknown data, right? So in this particular case, we say the variance is very high, whereas the bias is very low. Why do I say bias is very low? Because whatever example that we are giving, the example is giving to both the models, it is giving the as correct as the actual output, right? Because it has learned the examples very in a very well mannered, right? So we say that the complex models have the high variance, whereas with a low bias. Now, which type of model to prefer? Usually, it is neither we prefer simplistic model or simple model, nor we go for referring the, or not we prefer the complex models, right? Because simple model they only use the as they are not even good at training examples. They are not giving the correct result on the training example. So it will not, there is no question of giving the correct result for the unknown or unseen examples, right? Whereas why not to prefer the complex model? The complex model, if we design and develop, then what happens? It may give very 100% result accuracy on the training examples, but for unknown example, it will not give the correct result. So what we ideally do, we do take the intermediate form of both the model. That means the model complexity we keep as moderate as possible, so that it should be able to give the correct result on the training data, as well as if we produce some, or if we give some unknown data in that particular case, also it should be able to work good, right? So in the, how do we go for achieving, or how do we say that yes, we have achieved the good results and now we have to stop training? So in that particular case, again, there are various approaches. One of the approaches, you start checking the loss, right? The whenever you're checking the training loss, okay, suppose the training loss is going to be 0, right? And definitely in the initial epoch or in the initial iteration, the training loss may not be 0. With respect to each update, with respect to each epochs, right, the training loss will decrease. Initially, the training loss may be supposed 2, and later on 1.99, so on, so on. With each iteration, it is expected that the training loss will be reduced. So in parallelly, what you will do is you will go for watching the validation loss as well, right? Suppose the test loss or validation loss, if it start increasing, okay, in that particular case, what you do is you go for taking the decision, yes, because even though training loss is decreasing, but validation loss is, once it started decreasing and later on it is taking the it is increasing. In that particular case, we will stop at that particular epoch, and definitely what we can do is we can go for stopping the training, right? So now by this time, it should be clear to you, because whenever you are doing certain kind of like model training, in that particular case, you have to watch the validation loss as well, because what happens whenever, even though if you look into only the training loss, and the loss will get reduced to 0, but there is no if it is not giving good results on the unknown data, so in that particular case, what you are doing indirectly, you have overfitted the model, right? So overfitting need to be reduced. In order to reduce the overfitting, you have to keep watch on both kind of loss functions, right? Okay, one of the query here is, ma'am, in practice, is it advisable to model the data on sample data set and then scale the model on whole data in place of actual full data? Or it is good for modeling on complete data set? I'm asking this because for finalizing the model, we need to do a lot of iteration, which requires huge amount of complete resource and hence lots of energy consumption when doing so on whole large data set. Okay, so with this, Mr. Pranod Kumar has asked this query. So in this particular case, always try to divide the data set into 3 chunks. One chunk, major chunk, you use for training the data set, and next chunk, second chunk for validation, whereas for the third chunk you will keep for the test data, right? So in this particular case, the usual, what do you say, the ratio is either it can be 60-20-20, or it can be 70-10-9-20, and so on, depending on your requirement. Even though the question seems valid, because more we need, if I want to train the model on the huge data set, then definitely the computation resource requirement is very high. So what is suggestible is, if you train on very small data set, then definitely it will lead to overfitting, right? In order to avoid that, you need to introduce more and more data, right? This is unavoidable situation. If you want to solve some problems with the help of deep learning approach, in that case, definitely you have to consider very huge, large amount of data set. Then only we can say that yes, my accuracy at the end of the day will be achieved. Whatever we will be achieving, it will be very good, right? Otherwise, what happens if I only try to like train the data on small data set, because examples are very few and parameters are very high, so it is very much likely that we are going to overfit the data. So for that sake, try to train on as many example as possible, right? Okay. Chat box. Okay. If I'm not able to see any kind of queries now. Okay, one more query related with again data set. How large data set would be sufficient for any particular work? Is there any way we can calculate beforehand? So in this particular case, definitely as of now, we cannot say that is this much amount of data set is sufficient, but it is always advisable, whatever data you have, okay, that data, try to collect the data as much as possible. Start the problem solving only when you have large amount of data in case of deep learning problem. Otherwise, whenever you are training the examples, you will get very good results. For unknown data set, again, it will be tedious to get the result, because you have trained the model on very small data set. And there are various approach using which you can increase the data set. For example, suppose you are, first thing which is advisable from my side is, you have to use on large, you have to always use large or huge amount of data for training. And for some problem, suppose you're not able to collect the large or huge amount of data, then what you can do is, you can go for some sort of augmentation techniques, data augmentation techniques, right? Thereby, like, uh, given any image, right? If we are taking an image classification or image classification example, let's say, so in that case, taken the image, what you can do is, you can create copy of that particular data, single data set, single image itself. You can create multiple copies by either enhancing the image, okay, increase the brightness, decrease the brightness, or else you try to scale up, scale down, or you try to rotate the image, okay. So by performing certain set of transformations, what you can do is, you can achieve the good amount of data set. For example, if I only perform the rotation to 30-degree, and I have 10 examples with me, then I will take, with respect to each example, I will take the example first image, and I will create 30-degree rotated image. So with each example, I'll be having two examples by simply performing rotation, right? Like this, if I have 10 example, I can increase to 20. Like this, you can apply various other transformations or data augmentation techniques, and you can increase the data. Okay. Fine. With this, I'll close the session. And if you have any further queries, you can post it on the portal. We will try to answer. Right. Thank you so much for joining us.
Thank you, ma'am.